So now that we've defined equivalence relations, we need to talk about what happens with a relation that is not an equivalence relation, or does not satisfy all of the things that an equivalence relation satisfies. And this is when we have to now define the closure of a given relation. Given any one of our properties for relations, we can actually close the relation under that property by adding all of the elements that that satisfy or make the relation satisfy that property. So we say that if a relation R is defined on a set A, and the closure of the relation R with respect to some property P is the relation on A with property P and we'll call this new relation RCL, maybe even just RP, to denote that it is a new relation that has property P that contains R so R is a subset of RP and is also, so RP is a subset of every subset of A cross A containing R with property P. So it turns out that the transitive closure is typically the closure that is the most difficult to calculate. So we're going to start by talking about the reflexive closure, which is the easiest to consider. The reflexive closure of a relation R is called, or is denoted and computed as R union the diagonal relation, R union delta, where delta is the set of all A comma A, which that A is an element of A, and is called the diagonal relation on A. And there are a number of good examples of computing this in the book. However, I'll just consider the example that we considered earlier in the lecture, which is the example on the four elements at A, B, C, D with the relation A comma B, A comma D, B comma B, B comma D, C comma A, C comma B, and D comma B. The matrix representation of R is the matrix 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0. And we also saw that we can do a matrix representation or a directed digraph representation as well. So I'm going to draw both of these because both of these can be used to figure out the closure for any one of these given properties. So this is the digraph representation of the relation R. This is A, B, C, and D, and we have an edge going from A to B, an edge going from A to D, directed edge going from C to B, from C to A, one going from D to B, one going from B to D, and then lastly one loop corresponding to BB. If you look, the number of ones in our binary matrix representation is equal to the number of elements here. You have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then in terms of the edges, you have 1, 2, 3, 4, 5, 6, 7. Right? And each one of these edges is chosen to come directly from the relation. It's not too difficult to see for this example what the closure is going to be, the reflexive closure. If we copy all of this right here, the reflexive closure we're going to get when we add in the elements A comma A, B comma B, and D comma D. Right, and this is the set R union the diagonal relation. This can be directly seen in both of our representations here. For the matrix representation, what we need to do is look at any of the diagonal right here and add a 1 wherever we have a 0 on the diagonal. So each one of these added elements corresponds to a 1 in the diagonal, and in the digraph representation it represents adding a directed loop on each one of the vertices of the graph that didn't previously contain a loop on. But this very clearly shows how to construct the reflexive closure of this example relation. we have a reflexive closure, and then we also must have a symmetric closure as well. The symmetric closure is defined as follows. This is a new relation, and if this at R union R inverse, and R inverse is what's called the inverse relation of R, which is actually for relations a lot easier to define than for functions. For relations, the inverse relation will always exist, and it's defined as follows. Instead of all B comma A in the Cartesian product of A with itself, such that A is related to B, or A comma B is in the relation. And this is very, very neat, because this directly gives us a way of, for any relation, closing it and making it symmetric. So this is a very useful tool here, both of these representations. I'm going to jump back to the example to kind of show how to use the representations here. And for the previous problem, I just formed the direct union, but I'll show you now how to use both of the representations to write this new matrix down. So the binary matrix representing the closure for symmetric closure will be R union R inverse, R union R inverse, and then this setup here is going to be R union R inverse. The elements that we have to add here are now going to be elements that are across the diagonal. And anywhere that you have a 0 and a 1 across the diagonal, you have to change the 0 to a 1. So this element right here will become a 1. This is a 1 right here, so this element right here will be a 1. There's a 1 right here, so this element should be a 1. And now this matrix becomes a symmetric matrix, which means its transpose is equal to itself, and we directly get any and all elements that we have to add to make this relation R now be a symmetric relation. So R union R inverse is a symmetric relation. You can also clearly see that this is going to correspond to adding the element B comma A, which corresponds to this directed edge right here. We have to add the element C, or B comma C, which will be this directed edge right here. And then lastly, we have to add the element A comma C. Which will be this right here. Oh, and I also just realized I missed one of my ones here. So this is why both of the representations are kind of helpful here. You can add a 1 right here to make it symmetric across this element as well. And that's going to correspond to adding an edge D comma A right here. So we have to actually add 4 elements. We have to add B comma A, D comma A comma C, and B comma C. And the addition of those 4 elements will now make this relation a symmetric relation. And I think this very clearly demonstrates the concept of symmetric closure of a given relation. So the final closure that we're going to talk about in the lecture today is going to be the concept of the transitive closure of a given relation R. And before we can do this, we have to define what's called the connectivity relation, and specifically to do this, we're really going to use the idea of directed graphs to help in the construction of these closures, the transitive closures. And so we define the following for a given directed graph. So that a path from A to B in the directed graph G, which is the combination of the vertex set A and the relation R, is a sequence of edges x0, x1, x1, x2, x2, x3, all the way up to xn minus 1 comma xn, where n is a non-negative integer and x0 is equal to a and xn is equal to b. Another way of saying this is that it's a sequence of edges where the terminal vertex of an edge is the same as the initial vertex in the next edge of in the path. The path is denoted by all of the vertices that lie in the path. So x0, x1, and so on and so forth, all the way up to xn, and has length n. And what's interesting here is you can view the empty set of edges as a path of length 0 from A to itself. A path of length n greater than or equal to 1 where A equals B, or the starting point equals the ending point, is called a circuit or a cycle. depending on what paper or text you're reading from. But what's interesting here is this concept of a path for a directed graph is directly related to the concept of relation, the underlying relation that's the directed graph is coming from. We can really think of a path as a subset, a very special subset of this relation that connects A to B in terms of the nth power of the relation. And this gives us the following theorem, which is let R be a relation on a set A. There is a path of length n, where n is a positive integer from A to B if and only if the ordered pair A comma B is an element of the nth power of the relation. And the proof of this theorem can be done very straightforward using mathematical induction. And so I'm not going to go over the proof of this right now, but it's definitely a very interesting application of induction. And this is in the book in chapter 9.4. So I recommend taking a look at it if you're interested in seeing another example of an induction proof, and kind of seeing how important this concept of mathematical induction is. But using this theorem and this idea, we can go ahead and directly define what's called the connectivity relation on a given relation R. And this is the relation that we're going to need to use to close a given relation R transitively. So if we let R be a relation on a set A, the connectivity relation consists of the pairs A, B, such that there is a path of length at least one from A to B in R. And we denote the connectivity relation R star and we can always compute this or define this by taking the union of all powers of the given relation R. this is a super useful relation in many models because it directly gives us a way of taking a relation that may not be super connected and figuring out which elements we have to add to it to make it more connective or fully connective, fully transitive. And we're going to see very soon that this is directly related to the transitive closure of a given relation. In fact, it's equal to the transitive closure. This is Theorem 2 in the book, in this chapter. So the transitive closure of a relation R equals the connectivity relation R star. So this is a very important theorem. The proof is not too difficult to go through and do, and I'm not going to go through and go over the proof right now, but again, this is in chapter 9.4 of the book, so if you're interested, this is where you should go to look at this proof and understand it. And it really just kind of relies on all of our definitions of transitive and the definition of this connectivity relation R star as this infinite union. Going one way is relatively easy, right? It's simple to show that R is a subset of R star because it's a union, and R, the first power of R, is by definition in the union. So showing that R is a subset of R star is very easy. However, going the opposite direction is a little bit more challenging. But this is detailed in this proof in the book, and if you have questions, let me know. I can go over these. But the main important lemma that we have and that we're going to use for actually calculating this transitive closure on a finite set, right, finite relation, is super useful and super needed in terms of actually going through and being able to say compute the transitive closure using a computational algorithm, which is something that I've done up in Python code that I'll post to the Canvas for the course or course Canvas page. And in order to do this, we actually need a theorem from chapter 6 in the book, which is basic counting or combinatorics, called the Pigeonhole Principle. And this is that if k is a positive integer, and k plus 1 or more objects, you can think of these as elements of a set, are placed into k boxes, or other subsets maybe, just one by one by one, then there must be at least one box or a set that contains two or more of the objects. And the proof that this is relatively straightforward, I will go over the proof right now to kind of show it to you, but before we do that, the intuition here is that if I have, say, a set containing A, B, and C, and I only have two sets, S1 and S2, that I'm going to be putting all of A, B, and C into, at least one of these two sets has to have two objects, or more than one object. So for instance, you could put C into S1, B into S2, but A has to go into either S1 or S2. So either S1 or S2 will have more than one element. And this is a very important, even though it sounds relatively straightforward, it's a very, very important counting principle that we need to use in many proofs in mathematics. So the proof of the Pigeonhole Principle can be done by contraposition. Which is to show that the Pigeonhole Principle is an if-then statement, or a statement if P then Q. So for a proof of contraposition, we're going to be looking at the logically equivalent statement of not if not Q then not P. And what we do is that we suppose that none of the K boxes or sets contain more than one object. Or element. Then the total number of objects would be at most K. Which means that statement P, which is K is a positive integer and K plus one or more objects are placed into K boxes, is a false statement because the total number of objects would be at most K. So that means that not P is true. And therefore, because we've just shown that not Q implies not P, then we must therefore have that P implies Q. This is kind of a neat contraposition. You could also use for contradiction here as well. but the idea here is that this is good enough proof of this, and this is a very useful principle because it's going to be directly used now in the following lemma. This lemma is going to help us to not have to consider this infinite union, right? In general, this works, but we want to be able to do this on a computer, and for large relations, form connectivity information. Say for a social networking site, trying to analyze data between users about connectivity information. So the lemma here is the following. Say let A be a set with n elements and R be a relation on set A. The lemma says that if there is a path of at least length 1 in R from A to B, then there is such a path with length not exceeding the number of elements in the set n. This is basically saying that if we have a finite set A of elements, and R is a relation on that set, then there's a path of at least, if there's a path of at least length 1 in R from any two elements, from A to B, then there is such a path with length not exceeding the number of elements in the set. Moreover, when A is not equal to B, if there is a path of at least one in R from A to B, then there is such a path with length not exceeding n minus 1. So the idea here for this lemma, the importance of it is that it allows us to really simplify that union from an infinite union, right, of all of the powers of Rn to just being a finite union up to the final the number of elements in the set itself. So it definitely cuts down on the process of going through and computing this connectivity relation. And to do this proof, we'll start with the first part of the proof. This is, we'll suppose there is a path from A to B in the relation R, and we'll let M be the length of the shortest such path and specifically we'll just suppose that this path goes from x0, which is A, to x1, x2, and so on and so forth, all the way to xm minus 1 to xm, which is equal to b. So this is the length of the shortest such path from elements A to elements B. So for the first part of the proof, we'll also suppose that A is equal to B, so this path is a cycle, and that M is strictly greater than N. Right? We know that this also means that M is greater than or equal to N plus 1. And what this is saying is that the number of edges in the shortest path between A to B is greater than the number of vertices in the directed graph, or the number of elements A in the relation. And this is where the pigeonhole principle is important, because we say by the pigeonhole principle, because there are n vertices in the set A, or n elements in the set A, among the m vertices in the path, which is x0 to x1 all the way up to xm minus 1, at least two of these vertices must be equal. And the idea here is that if you have less elements in your set A, right, than you do in this path, this path, the shortest path between vertices A and vertices B, right, you're trying to put m things into a set of size n, and if m is strictly greater than n, right, the pigeonhole principle says that at least two of these things must have more than one value in it. So it's a direct application of the pigeonhole principle. You have these m things that you're putting into right, each one of these x0, x1 up to xm minus 1 must be elements from the set A, or vertices, and if you only have n elements A to choose from, then at least two of these vertices must be equal. And this guarantee is very neat, because it's the crux of this proof. Let's suppose that we have two separate xi and xj in this path, such that vertex xi is equal to vertex xj. then the path so this full path must contain a circuit or cycle from xi to itself. We can delete this circuit from the graph or from the path from A to B, leaving a shorter path. Which is a contradiction, because this means that m is not greater than n. If we delete all of these cycles, we can obtain a path of maximal length of n, where n is the number of vertices. Therefore, m, the length of the shortest path, must be less than or equal to n. So this concludes the first part of this lemma, as proof of the first part of this lemma. The second part is very, very similar. And the second part of the proof is relatively straightforward to go through and do. It's the exact same argument, only a little bit changed, because you have to argue for not a cycle. In this case, we're arguing for a cycle where the endpoints A and B are equal. You have to go through and do this exact same argument for just a path that's not a cycle. So A is not equal to B, but when you do this, you get the second part of this lemma, which is that when A is not equal to B, if there's a path of at least 1 in R from A to B, then there is such a path with length not exceeding n minus 1. The general structure of the proof is exactly the same, so it'd be a good exercise to go through and prove this for yourself. But the idea here now is that we can use this to get a great simplification for our computation. Right, from lemma 1, the transitive closure on a finite set A can be computed by taking the union. I'm going to use a different index here for the union than I did before. It's the union from k equals 1 to n of the kth power of the relation, or R1 union, R2 union, and so on and so forth, all the way up to Rn. Okay, note the difference from before. And I'll change this to k to make this a little bit more consistent in the notes. The union from before was an infinite union, right, for a general set R. However, for finite sets, what we've shown using some basic graph theory is that we only actually need to consider a maximum of the number of elements in the set itself when we're taking the union for this transitive closure. This is because of lemma 1 right here on the path length. and this is super important because it lets us go through and say definitively that if MR, so we'll let MR be the matrix, the 0, 1 matrix that represents the matrix or the relation R on a set A containing n elements, then the 0, 1 matrix of the transitive closure R star is computed as follows. We take the OR operation of each of the Boolean powers of the matrix MR. Or it's MR or operation, the second Boolean power of R, all the way up to the nth Boolean power of R. And we've actually already seen this a little bit earlier on, but this now is proven for us for a general relation of any size. And I will go through now and consider our previous example. We take the relations from this first example that we considered. We'll go through and show how to compute the transitive closure of this example. So the original matrix is this MR. The Boolean powers of MR can be relatively straightforward to go through and calculate. The second Boolean power is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. This is the Boolean product of MR with itself. And what's rather nice for this example is that the other Boolean powers are also the same. So this ends up actually repeating itself indefinitely after the second Boolean power. But what this means then is that if you take the OR operation of each one of these Boolean powers, so MR or MR2 or MR3 or MR4 you'll obtain the matrix for MR star, which will contain an extra 1 right here and an extra 1 right here. Or in terms of the graph, an extra loop right here and an extra edge right here. Which corresponds to, for the original relation itself, adding just those two elements to the original relation from this example. So the closure relation for this, for the transitive closure relation for this relation R in this example is, we're going to add the element DD and the element CD. And this new set forms the transitive closure of this relation. So this is super useful, and it directly gives us a direct algorithm for computing this transitive closure. And there's also a nicer algorithm called Warshall's algorithm, developed by Stephen Warshall, which is actually faster than this standard algorithm. So when we talk a little bit about algorithm speeds, I'll get into describing Warshall's algorithm a little bit and talk about how it's a little bit better than this standard algorithm that you just directly uses this this relationship right here. So the calculation of the union of all of the Boolean powers of the matrix R, or MR. But what I want to do to finish the lecture is to kind of show a result of using this computation for relatively large matrices. So what I'll do is consider a random relation that I use a random number generator to generate, and just kind of pictorially show what this looks like. What I'm going to do is I'm going to start with a random relation that's not symmetric, reflexive, or transitive, and then just form each one of the closures to show you that you can kind of do this very nicely, visually speaking. This is for initial random relation with 10 elements, and you can see that it's not transitive, it's not symmetric, and it's not reflexive, which is a little bit harder to see, but it's not reflexive either. So what we do if we want to make an equivalence relation on a finite set is first form the reflexive closure, which involves adding elements on the diagonal. In this case, the I and the J here represent the entries in the matrix that represent the relation. So if the initial relation is this right here, you have a 1 right here in the I4 J0 component of the matrix, then the transitive closure, or the reflexive closure, is going to be having a 1 along the diagonal of the matrix. And then what we do is we take the symmetric closure of this relation and this ends up looking like this. So we have to add in ones on the matrix that are symmetric across this diagonal, the diagonal of the matrix. And the last step then is to go through and compute the reflexive, symmetric, and transitive closure. So then take this matrix right here the matrix that represents this relation, and go through and form the Boolean powers of this matrix and take the OR operation between all of them up to 10 in order to form this closure. And when we do that, this is exactly what we get right here. So you see that it fills out a lot, and what you're seeing here is actually kind of another representation, a visual representation of equivalence classes that are appearing here. Specifically, you have that if you have 10 elements in your set, that's going to be A is the set, A0, A1, A2, all the way up to A9. And you have that the equivalence class of A0 is the set containing A0, A4, and A5. Because A0 is equivalent to A4 and A5. You then have an equivalence class for A1, and so A1 is equivalent to A1 itself, A2, and then A6, A7, A8, and A9. And then the last thing that we got to look at here is what A3 is equivalent to. And A3 is equivalent to just itself, because this is the only one that we have in our matrix in the row corresponding to A3. And so if you form the quotient set A mod R, for this example, the quotient set is going to be the set equivalence class for A0, the equivalence class for A1, and the equivalence class for A3. And we directly have that we can kind of see this partitioning that we're getting when we form the reflexive, symmetric, and transitive closure of this initially chosen random relation. And I'm not going to go through and show the partitioning in depth like this for the next couple examples, because they're going to be quite a bit bigger, but it is kind of cool to see. So let's raise the number of elements in the set up to 100, in which case this is a randomly chosen relation, where each one of the black dots here, just like before, represent a 1 in a specific entry in the matrix R that represents the relation, forming the transitive closure of this relation. Will give us this picture right here. You see this is equivalent to adding ones along the diagonal. Forming then the symmetric closure of this relation involves adding in all of the elements that are across the diagonal for this relation right here. And you can see very nicely that this becomes symmetric matrix. And then the last step here is running through an algorithm that implements the previous connectivity relation and we see very, very clearly the partitioning that happens in this set through this equivalence relation, just like before. Now, going through and getting the equivalence classes for this would be very, very complicated, but it's feasible to do, and we're directly calculating this using the process that we've talked about before. This is really neat. And I'll just give one more picture here. We'll bump n, the number of elements in the relation, up to 200 to show that we can go through and directly do this procedure regardless of the size. So this represents the randomly chosen relation on 200 elements. This is the reflexive closure of that relation. This is the symmetric closure of this relation. You can see very clearly that all these points, the ones in this matrix, are symmetric. When we form the transitive closure, it really fills in the matrix. But you can see very clearly the partitioning that's going on into different equivalence classes in much the same way as we talked about before, which is really, really cool. So this is directly calculated from Python code that I wrote, and I will post to the Canvas page so you guys can take a look at that and kind of experiment with that if you're interested. But this is going to conclude the lecture on relations. Thank you all for tuning in. I hope you learned something and you had a fantastic day.